I'm based in Derby in the Dynamics Gauging and Testing team. So I'm here today to talk to you about Vampire and the Permanent Way. What we'll go through today is we'll talk about railway vehicle dynamics, how that relates to Vampire, how Vampire models the Permanent Way, and then we've got a couple of case studies, recent bits of work that we've done. So first up, what is railway vehicle dynamics? So dynamics is the study of masses in motion. Yeah, so very simply, masses, springs, and dampers. When we talk about vehicle dynamics, this is how vehicles behave in motion as masses. So that can be road vehicles, rail vehicles, air, sea, space vehicles. What's different about railway vehicle dynamics is we've got a steel wheel on a steel rail. So that contact pressure is, for those of you who don't know, it's something in the region of an elephant standing on the head of a drawing pin, which is the highest contact stress in engineering, which makes modelling very complicated. When we're looking at railway vehicle dynamics, we cover modal frequencies and damping, look at things like ride quality, derailment risk, wheel wear, rail wear, gauging, to name a few. I'm sure you can appreciate it's a complex subject, so we need some specialist software. Just lost my mouse, just click on. There we go. Right. What is Vampire? Has anyone in the room heard of Vampire before? Yeah. Good. So Vampire is a multi-body simulation package designed for railway use. Based on equations of motion, it's a simplification of a very complex system. It's masses which are joined together by suspension elements. In this case, it's springs and dampers. So a simple vehicle model will have 7 masses. So you've got a car body, 2 bogies, 4 wheel sets, and these will be joined together by combinations of springs and dampers. So for these masses, we need inertias, centre of gravity positions for all of them. The suspension elements, we're looking at springs, dampers, other things like anti-roll bars, bump stops, bushers. And these are all simplified into essentially stiffnesses and damping parameters. We also look at different conditions, so we'll look at tear and laden, new and worn wheels, inflated and deflated air springs. Vampire has its history back in, I think, the late 70s, early 80s. It was initially a bunch of different programs, and then brought together as Vampire, with a unified front end and a single vehicle model format in the late 80s. And then the developments continued throughout different companies. So it's been in the hands of BR Research, AA Technology, Delta Rail, and Resonate. And in that time, it's been licensed to users all over the world. 2019, Resonate decided to sunset Vampire. So they Resonate's core business at that time wasn't really vehicle dynamics. So they decided to sunset Vampire, as they called it. Offered people perpetual licenses or developer licenses, eventually an exploitation license to allow somebody else to continue with commercial licensing. So they sold 3 of these exploitation licenses, one to SNC-Lavalin, one to Olio, and one to Ensco. Since 2019, Olio has used Vampire to develop their digital trains tool, which has some improved graphics, and some methods of quickly modelling track and handling some of the data, but they've not actually updated the main code. Entico is offering Vampire as a software as a service online. We don't think they've developed the code. As S&C level as we were then, back into Realis as we are now. We've added inline contact calculations and improved line elements, which we'll talk about later. And our next big release, which is happening soon, will be to include the advanced contact model with cloud licensing. So by cloud licensing, we mean that I don't know if anyone's used Vampire before. It used to be that you have to have to use it, you'd have a dongle that you'd have to plug into your computer to get the license to work. So with cloud licensing, we do aware of that. This year, we've also provided a free version for people participating in the Armaki Railway Challenge. So I think there's a requirement there to do some simulations. This image here is of a bogie and Vampire. You can see that we've got wheel sets, springs, dampers, air springs. So those are all representations of all the elements used within a bogie. You can see the vehicle model is one part of Vampire. Another part of it is what inputs we give to it. So we can look at track design, geometry, and irregularity. We'll come on more to those later. We can apply traction and braking forces at the wheel sets. We can also apply external forces, such as when loading or inter-vehicle forces. In terms of outputs, we look sometimes at body accelerations and displacements. So typically, if we look at ride comfort, body accelerations would be used to look at ride comfort. Suspension component forces and displacements. So that could be looking at what happens if you have a failed suspension component. If you're a vehicle manufacturer, you'd be looking at that for looking at kind of what forces would go into your suspension components over a lifetime. Bogie accelerations and force inputs. So that might be looking to see if a bogie's behaving as it should be. Real rail forces, those can be used to look at how quickly something's predicted to wear, or if there's some unusual wear patterns being observed to try and explain them. And then we can also look at safety against derailment. So that's things like wheel unloading, flange climbing, also known as YFQ, or vehicle rollover. So just talking to us earlier about TrackX. A few people nodding here. So TrackX is a network rail developed track management tool. It was developed to provide wider access of a network rail to Vampire type outputs for wear and RCF modelling, and to reduce the cost of Vampire licensing. So it produces approximate wear and RCF damage predictions based on track geometry, vehicle damage matrices, to look at tables of Vampire curving results for different vehicles and conditions, and it has algorithms to approximate damage based on the track alignment. It provides a good approximation, but it can't give the same details of full dynamic simulation of Vampire. If your vehicles change, or if your wheel well profiles change, or if you want to consider a worn wheel profile, worn rail profiles, it can't help you there. So why would you use Vampire for permanent way projects? With Vampire, we can predict parameters that are affected by track design. So looking at forces on track and the individual rails, look at the risk of high rates of rail wear or RCF, see what happens if you had flange lubrication, look at the derailment risk, whether you need track rails or not, look at the rate of change of cant efficiency and passenger comfort. And all of this allows the track design to be optimised in terms of vehicle track interaction. How does Vampire model the permanent way? So firstly, we've got what's called a truck design file. This models how the truck should be. Usually creates manually to model curves and gradients. So with curvature, vertical offset, cross level, kink, and speed channels. You can use metric or imperial units. Generally only North America, which uses the imperial units. So here we've got 3 channels. So we've got curvature on the top, cross level or cant in the middle, and vertical offset. So we've got it's a 25 kilometer truck file. So you can see from the top line it's fairly straight, but there's a few 500-meter curves there. And that we've got corresponding amounts of cant which are installed at the curves. And the vertical offset is to acknowledge that the inner rail stays at the same level. I go through the curves, it's the outer rail which is raised for cant. The other part of this is the track irregularity file. This kind of gives you the deviation from perfect for your track. So usually we will get information from track recording cars, such as the new measurement train, and we'll process that to give the output the channels Vampire uses. So we've got cross-level, curvature, lateral, vertical, gauge irregularities. Again, geometrical or imperial. So here we've got a trace of all 5 channels. These are normally measured every 200 millimeters or so. This gives an idea of how rough the track is. And we can replicate what the track is. Yeah, we've got a recent track recording. We can use that and we can replicate it quite closely. Other features. So we've got can also model track rails. Some of our newer format files can also put in other data in the files Vampire will ignore. But, so we can give ELRs and track ID to help to reference it back. We can also have a separate speed file. So that means there is a channel for speed in the design file. You can use or not use. You can use a separate speed file if you need a variable speed profile. Okay, so moving on to the wheel and rail profiles, we can use several different formats. Vampire formats, generally you get both wheels or rails in the same file. Many formats, you get one wheel or rail at the same time. Whichever Vampire can process them into making what's called contact data, which I'll come on to next. Generally, our Vampire files are kind of your design wheel profile or design rail profile. And the mini-prof files are what's been measured by a mini-prof. I guess you guys know what mini-profs are, don't you? Right? All right, okay. So mini-profs is a tool which is used to measure wheel and rail profiles. So you run a head across either the wheel or the rail, and it gives you a very high definition recording of the wheel and rail profile.
I'm using the real.
Yes, yeah, that's right. Yeah. There is another tool out there called Calibri, which uses a laser-based system, so that can be used. And those profiles can be extracted and used in Vampire as well. So then we've got the wheel profile and the rail profile in Vampire. One of the things that Vampire is very good at is it creates, as part of your pre-processing, you create something called a contact data file. This is where it kind of meshes the wheel and rail profiles together, taking account of gauge, wheel diameter, and axle load. And it gives you a big lookup table. So you've got positions, angles, forming radius, contact patch areas for each wheel, rail, lateral shift, So kind of as it moves, so the wheel moves further to the rail. Because you've got this big lookup table, during a transit simulation, Vampire just refers back to that table every time, which means the simulations run really, really quickly. We can use different contact data for different wheel sets. Yeah, if you've got a new wheel set on your first axle and then one on your second one, that can be modelled. You can also vary the contact data along the track. So if we're going into a tight curve and your rail profiles are changing, that could be modelled. So yeah, there I've got a few outputs from that contact data file. Something we've recently added to Vampire is the ability to do what's called inline contact data. So this is actually making that lookup table for every time step. So this allows a high level of accuracy, but it's much slower. So typically you'd only look at it for a very short distance using this, just because it takes so much more time. As I mentioned earlier, our next release of Vampire will contain it's called the contact model. This has been developed by another party, but that's a very highly detailed wheel rail interface model. So that will allow things like wheel flaps and data rounds to be modelled. Again, very highly detailed. The truck is modelled again using stiffnesses and dampings. So we have a vertical stiffness and damping for the whole track. But each rail has its own stiffness and damping, and the sleeper has a stiffness and damping, as does the truck rail if it's modelled. We've got default values, but these can be varied. So you can change them for a whole simulation or for just a specific part of the track. So if you're modelling a wet spot, for example, you could quite easily model that by changing the track parameters. And it also allows us to change the wheel rail friction as you go along the track. So that's the first part of the presentation. Now I've got a couple of case studies where we've worked on. We've helped permanent way people. So first up, we've got 11-mile link, 5-mile railway that was returned to use, get opened June last year. So my colleague Owen, he did a lot of work on that, using Vampire to model the track and to model a couple of the design iterations. He was able to show that the final iteration showed a reduction in cant excess and twist. And that's a plot of the final version. And here we can see that the version 4 and version 5. So version 4 is in red and version 5 is in green. The reduced installed cants, which means that when trains running slower, there's less cant excess. They looked at lots of different vehicles. We looked at the Class 66, Class 156, Class 380. Although the truck is not electrified, it's planned to be electrified. And also a container wagon with a white 25 baby. Simulations are used to predict cant excess, cant efficiency at the chosen speeds, rate of change of cant efficiency, derailment risk. So looking at wheel unloading, wire for queue, flange climb, looking at truck shifting and gauge spreading forces on the curves, and looking at wheel and rail wear numbers. One of the things that Owen did was to look into the effect of truck rails. So the group standards say if you have curve radii between 200 and 300 meters, You don't necessarily need truck rails, but you need to be confident that you can get away without them. So you need to do a risk assessment. This is the sort of thing which Vampire is really good for. So what I managed to show was that using Vampire was that the derailment risk was low, so the truck rails weren't needed. Saved a lot of money. Yeah, so I think future things that we could look at. So we could look at the effect of any truck design changes, look to optimize the line speed, do energy calculations, see how much energy is used up in the wheel rail interface, and look at other vehicle types. The benefits of the project. There's confirmation that the truck design version 5 was better than version 4. And as I mentioned, the truck rail assessment showed that truck rails were not needed, which was a major cost saving. That's Leavenworth. And then our second case study is Doddston Junction. So this is one I've been working on. So, sure if you can see it all that well, but this is just outside Birmingham. So you can see the newly realigned track on the left-hand side. It's kind of, I've had to move it to put in a support pillar for an HS2 viaduct. The photo I took on the right-hand side, you can see just how curvy the track is. All in all, there's about 500 metres of realigned track. Very quickly, they showed that there was some severe wear, lipping, and RCF. So we used Vampire to model the track geometry for the realigned track. Went down to site. In fact, I've been there twice now to observe and to measure the one wheel profiles. So the mini prof tool I was talking about earlier, we got that and measured the rail profiles every 10 meters. So we've got some of the worn rail profiles measured on the right hand side there. At the far right, you can see where there's a bit of blipping. In fact, when I went back there recently, that's got a lot worse. So we used all of that. We carried out a number of simulations. We looked at class 66 loco. We looked at 3 different wagon types. We looked at and modelled the wagons at 80 and 100% of payload to 4 different speeds. We looked at low, medium, and high wheel rail friction coefficients with and without flange lubrication. The first thing we saw was that our simulations correlate quite well with what we've seen on site, which is good. Gives you some confidence. We found the following trends in our simulations. We found that some vehicles were slightly better. All the vehicles showed propensity for wear and RCF. We showed that higher loads slightly increased the amount of wear to be expected. We found that speed was not a significant factor. What we found was that friction was the most significant factor. So if we could lower friction levels on both the tread and flange, that would decrease the wear, although there was a risk of higher RCF. So that graph on the right-hand side is the same vehicle running through the rear line track, same speed. The red line is high friction, the green one is medium friction, and the blue is low friction. And what's being output there is a term known as T gamma, which is the measure of the energy being expended in the rear rail contact. So what that's showing is that you'd be expecting a lot more wear for the red line with high friction. On the back of that, we made 3 recommendations. So the friction solution providers should be engaged to look at top rail friction modifiers and flange lubrication to reduce the wear. So in fact, that's happening now. That's been installed. Let's go and re-measure the rail profile to look at the wear rates, see what happens, see if these friction solutions are having a difference. So yeah, we've been back once, which was when they were installing the friction modifiers. We're going back there again in a few weeks to see if they've made a difference. And then our last recommendation was look at whether it would be worth it to install harder rails. based on the principle that rail RCF can be managed through regular grinding rather than allowing rail side wear. Okay, so that's everything I have prepared. So now we can move on to questions and answers.
Yes.
Thanks for
Thanks for that, Halley.
Wait a minute, we've got a problem with
sound. Do some put it. Sure, on your mic.
My microphone's on, should I turn it off? Okay, can you hear me online now?
Can we be heard online? Is the audio work?
Yes, we can hear you.
Yeah, okay.
Okay, yeah, apologies for that. So,
Yeah, so I'll repeat my answer to Mike's question about validation. So there was a benchmarking exercise carried out, I think at some point in the 90s, called the Manchester benchmark, where Vampire and some other software packages were benchmarked against real world tests. So, and anything that was successfully benchmarked at that time was considered to be of a high quality. I was also adding that when we make a vehicle model, we'll validate the vehicle model against test data when we can as well. I've got hold of it.
does anybody else have any more questions? I'll ask one. I was just interested to know what sort of clients you have within the team for to Vampire modelling. Is it mainly network rail projects?
Yes, we've got a whole host of clients. So we've got vehicle manufacturers. Sometimes a vehicle manufacturer might prevent our team. They might not have the resource to do it themselves. They might ask us to help them out of Vampire modelling. We've got people like networks, infrastructure maintainers. We've got operators. Kind of any problems with a vehicle track interaction, we can get involved and we can use Vampire to help them.
Yes.
Very specific learnings from the Duddeston example. Went out there and identified an issue you know, the causal factors where it could be shared to improve track geometry. So
Yeah, so the underlying cause was that there was a lot. It was very tight curvature. In fact, the site was very constrained. So the designers, I don't think they really had any other option within the parameters that were given to move that track. I think perhaps, and there were 2 tracks that were moved, and one of them actually is used about twice a week. So perhaps actually getting rid of that track and having gentler curves
yeah, sweet.
might have been better, even though accepting a bit of operational difficulty twice a week. Maybe that would have been a better solution. I don't know. Where you've got tight curvature, you're going to get where.
Some outside of it all.
Those curve radiuses were about 250, 260 meters. So
Not that tight. Did you do gauge widening, or was it just
no, there's no gauge widening.
So it was a combination of the tight curve and the heavy freight. Was it heavy?
Yeah, well, yeah. There's another factor there that I didn't really mention, was that at that point all the DB cargo trains stopped to change driver.
So you got acceleration and
Yeah, you've got acceleration and braking,
Yeah.
so that's increasing the wear as well.
Yeah. Braking?
There's a bit of a gradient. It's not a massive gradient.
You tend to model on attainable speeds with Wi-Fi when you do, or do you always just design to the full speed profile?
Depends on the situation. We can look at typical speeds, we can look at line speeds. It's fairly easy to change a number. Yeah, so for example, there's been supporting one client a few years ago where they were allowed to run on one route on speed, but they were hoping to be able to run it at higher speeds. So that was quite easy. So okay, let's run it at both speeds. That's the ride comfort at speed A and speed B. You can get both sets of results.
I did a project a while ago where we were being challenged quite heavily to try and save money, as we do nowadays, in terms of siding. We designed at 500, and if we could have steepened that siding towards the main line, we could have saved a lot of earthwork. Now, if you look at ready cows, now they're worried if there's been a brake failure, the train moving, and do its own load. And I did some stupid simple counts based on the friction to the bearing, and I counted it would never move. Could Vampire do something like that, to say fixed on only 100 and the brakes failed with the various coefficient of frictions you've got for wheel relevant bearing coefficients?
Yeah, so bearing coefficients are kind of not modelled themselves. What we are working towards is kind of getting something similar, so we get a whole train resistance for longitudinal movement. So that's something we're working towards. So in theory, with the right data, we could model that situation.
That would be a really useful thing to use, because that 500 is an absolute mare. I think that would be a really powerful development, because if you get that, then I mean, we could have done what I wanted to do, which was probably stupid. That we could have maxed it out, we could have probably saved cubic meters of dealing fill and all sorts. Big savings, take retaining walls out and everything. Could have challenged it. As soon as I said it, now people were producing stupid single counts, just said, well, I don't think I'll move. I said it won't move.
Yeah. Yeah, and a lot of design rules are based on kind of rules of thumb, aren't they?
It's from way back when the measurement got spring brakes or whatever, they're a lot less reliable than today. I imagine we used to get brake fails all the time back in the day.
Last call for any questions before we wrap up.
I have one there, so let's actually for you. On B here, on Crew, our limiting radius of check rail was 250, wasn't it? Not 2.
Yes, but that was a pre-reference.
No,
It's not in the standard. It was particularly relevant to crew because of dangerous goods, the nuclear flasks, and that's what they were worried about.
Do you reckon if we'd have done the vampire modelling, we might have proved that they were
Could possibly
check
use
rails?
that. Adjusted, yeah.
We had a track that was kind of weaving like that.
Yeah.
Check rails were a bit onerous, overlapping and so sides and stuff, and it was.
It was a pain, that check rail, because we need to put IRJs in and all sorts of things.
It's only 10 mile an hour as well.
Yeah, and aren't the nuclear flasks designed to be quite literally bulletproof?
Yeah.
Yeah.
It's
So,
I think it's
even if they derail, there's no risk to anybody, is there?
no, but I think it's not politically acceptable for derailments.
Yeah.
But I don't think it just go down in the press very close.
Yeah, it's good to know we can challenge stuff like that now.
Yeah.
Yeah, that's one thing I've really taken away from this talk, because I've always wondered how they justify not having a check rail because of that clause. Well, now we know where to come if we need help to justify.
Yeah, so in that instance, I guess we'd look at the track geometry and we'd model all the different kind of sort of vehicles that are going over that site. And look to see if they get anywhere close to derailing with a kind of a plausible combination of factors. And not necessarily looking worst, a plausible combination. And
Would that do a what if as well then? So you could take the check rail off, put lubrication on to avoid.
we can do all of that very easily. Once you've got everything set up, it's quite easy to play numbers.
Is that just rear rail interface as well? Not looking at gauging yet.
So, vampire, for gauging, if I say the term absolute gauging, do you guys know what I mean? Using Curie.
Yeah.
Yeah, so the vehicle models which are used from Curie, you've got different types of vehicle models, but the most accurate model is created essentially using a load of lookup tables that come out of Vampire.
Right.
So you have a vehicle model and you run a number of cases to kind of predict how much the vehicle is going to move. That produces a load of lookup tables, which are then used in Curie.
Yeah.
So say, on this curve, it's 500 metre curve at
This
50 miles an hour.
This
This is how much the vehicle moves.
It's clear, it just maximises all those lookups, doesn't it, to make sure absolute worst case.
Yes.
We're doing according with this is we've got a project at the minute where we've got some stupid clearances that are existing. And we need to get a new vehicle to scout. Make some fire-passing clearances. Yeah, I mean, it's there now, so it's clearly working. So just proving my long-held belief that clear route is slightly conservative.
So let's take this offline.
I did have one more thought. We've got time.
Yeah.
I was just thinking the derailment risk assessment, could you use that to prove whether or not you needed guardrails, collector rails on viaducts as well? Or is that something that you just meant to do because the standards say so?
My understanding is you need to have them because it's about trying to contain a train that's already derailed.
Probably not worth avoiding putting them in this.
There's that subjective assessment we need to do that because to be checks and subjective assessment first to say whether you think you need.
Do you always need the collector rails? Sometimes they aren't there.
You want to be collecting rails if you're facing, if you're going off the, well, that's my opinion, anyway. You need it if you're facing, not if you're going
on the entry.
To go back, I think both ends. Yeah.
I've noticed most viaducts I've been involved with for years now have got guardrails on already, so the precedent's set, you can't really get rid of them, and do a trapping.
Your hands don't go with that big embankment. Bit of a pickle there because the standard shows that through something to form the standard now says you need to do that enhanced derailment assessment. It's not pickle the hands up because we proved everything, so we demonstrated better. But we have to do a Piccadilly as well. That will be an interesting one. It's those parapets one. Taking it. Pretty standard that person to leave it.
Right, well, I think we'll wrap it up now, so most people are dropping off online. So, on behalf of the Cheshire and North Wales PWI section, I'd like to say thank you very much, Halley, for giving up your valuable time and coming here in the sunshine. I'm sure we'd all like to be outside enjoying the rare sun. So, yeah, that's much appreciated. And thanks for everyone in the room and online for joining as well and supporting the PWI events. It's much appreciated. And I'd just like to finish by inviting everyone in the room and online, if you want to do a virtual hand clap, or give Halley a round of applause. Yeah. And that closes our May meeting. So thanks everyone.